Okay, good day. So that will be our last formal lecture. All right. So today I will spend maybe 15 minutes to give you more examples of proving NP completeness by using method restrictions. And we'll talk about approximation algorithm. Just will give you a taste. All right. Okay, so let's consider the following problem, dense induced subgraph problem. So we want to find an induced subgraph in a graph with as many edges as possible. So let me give you an example. So that's input graph G. Okay, so I think that's big enough. All right, suppose in this graph, I want to find the induced graph on four vertices. So what we want is this graph contain as many edges as possible, is as dense as possible. Okay, so that's a problem. For example, for this particular graph, if k equal 4, I think the answer is unique. This graph contains 6 edges. That's the densest graph on 4 vertices. So that's a problem. Anyone see that this problem is NP-complete? Because it contains an NP-complete problem as special case. Oh, I forgot to list. Yeah, so in our toolbox, we have 3 set. Let me remind you, we have 3 set. Yeah, exactly, click, yeah. Okay, let's see, because sometimes there is small window popping out. Then the place I'm going to write, suddenly a window popping out. The 3 set. Okay, vertex cover, that's same as independent set, click. And then we have dominating set, Hamiltonian cycle, Hamiltonian path, and also subset sum. So that's the toolbox we have. We can use any one of them to show that a given problem, a problem we're going to prove, contain one of them as special case. So in this case, it's quite obvious. Click is a special case because by setting L equal K choose 2, we get a click. Densest subgraph we can obtain is a click. So very often when you want to use this method to prove NP completeness, the value we set for these things, typically we set it to be extremal value. So typically it's maximum or minimum or value in the boundary. Typically that's the case. All right. By setting its value to the boundary value, so typically minimum, maximum value, possible value for subparameter, we get an NP-complete problem. So in this case, by setting L equal K choose 2, we get click. Okay, so it's quite easy. So next one is, it's here, okay. Subgraph isomorphism. So input is a graph G, actually 2 graphs. I have a graph G, so that's graph G. It's a host graph and a guest graph H. All right, then, so this graph G, then I have a guessed graph H. Perhaps this is a graph. All right, so question is whether you can find a copy of H inside G. So it's a partial subgraph. Whether you can find some edges in G, which is exactly same as H. So here exactly means isomorphism. So these 2 graphs are isomorphic, have same structure. Okay, graph isomorphism. All right. So for example, for this one, I think it should be easier to find one, a copy here. Let's see. It should be quite easy to find one. So this is a copy of H. So answer will be yes, because this the red one is same as H. It's isomorphic to this H. All right. Similarly, if we talk about induced graph, in this case, it's not induced graph. Another problem is we can talk about induced subgraph. So instead of partial subgraph, here we can change to induced. So but for induced ones, this one is not. So red one is not induced one because it has this extra edge here. So for induced one, we should not have this this edge. Induced copy of this one, I'm not quite sure whether we have induced copy of this H. I don't know, okay, whether it contains induced copy. Okay, so that's the definition of problem. Now, let's consider the partial subgraph case first, subgraph isomorphism. Anyone see that any particular NP-complete problem is a special case of this one? Recall that our toolbox, we have these problems available. So these are problems that are available for us. Any suggestion? No, not vertex cover. Yeah, click. Yes, you're right. Click. Actually, there are a few problems that can be special case. One is click. One is click. So H will be a complete graph. So H will be taken to be complete graph on K vertices. All right. Another two problem is Hamiltonian path and Hamiltonian cycle. So we can take H to be a path on N vertices or cycle on N vertices. So both will be special case. So sometimes several problems may be special case of our target problem. So in this case, 3 problem fits. Now for induced one. How about induced one? Just induced subgraph isomorphism one. Now, can Z2 still be special case? For induced ones, these two do not work. They are partial subgraphs. So these are not. But the clique works. Also, another one is independent set. So in this case, these two do not work for induced one. So let me erase induced one. Okay. Another one is independent set. This one is also a special case. By taking H to be complement of a clique, we get independent set. So this technique is really very simple. What you need is really understand the problem. Once you understand the definition of the problem, you're looking for the extremal case. Usually, for the extremal case, you will find that is a special case of an NP-complete problem. Okay. All right. Okay. What do you mean? H isn't complete, right? What do you mean? I don't understand your question. What do you mean by H isn't complete, right? There is not a distinct edge. What do you mean? I don't understand. You mean this graph? Do you refer to this graph? I really don't understand your question. What do you mean? This is a complete graph. So if K equal 4, this one refer to this graph. So that's K4. And the K4 bar refer to its complement. So in this case, 4 isolated vertices. Okay. All right, so let's see one more problem on graph. The traveling salesman problem. This one is a very important problem, traveling salesman problem. So what we have as input is a weighted complete graph. So weight is from edges to say positive integers. All right, so it's a complete graph. We have all possible edges. For example, here is instance. Say 1, 2, maybe 3, 3, 4, 5. All right, so it's a weighted complete graph. Each edge has a weight. So our task maybe a tool. Let me put in this way first. Let's use a big one. Maybe use L. So input, other than this one, we also have integer L. All right, so it's very similar to Aurelian cycle, but now we want to visit vertices exactly once. So I can start here with this vertex once, then with this vertex once, then this vertex once, then this vertex once. That will give us a tour. And total weight of this one is 10. So we want to minimize the total length. In other words, we are looking for, what are we looking for actually? From different point of view. So the red one actually the forms, we're looking for a spanning cycle. Of minimum weight. All right. So in this case, you can say there's this kind of restriction a little bit different. Actually, you can say it's almost a restriction. What problem is special case of this one? It's almost. It's so here a little bit different. Hamiltonian cycle actually. All right. So Hamiltonian cycle, we have a graph. Actually, so if this is a graph for the Hamiltonian cycle problem, so we can interpret this one actually is part a subgraph of a complete graph. Now, if we assign weight for these edges each to be 1, all right, then non-edges, these edges not in the graph. So these edges, all weight to be 2, so all of them, okay, all each prepare 2, 2. So what we get is we get a complete graph. It's a weighted complete graph. So in this case, if we set L to be exactly n, what we have? We have a Hamiltonian cycle as special case. So you can say this one as a reduction, or you can say it's a special case. So this one is not exactly a straightforward, say, special case, but basically it's a special case. So in this case, it's a Hamiltonian cycle. All right. Okay. Is that clear? Good. Okay. Okay, yes. So again, that's a subtle point here. Here we're dealing with optimization problem. And sorry, we're dealing with the decision version of an optimization problem. Look how we describe the decision problem. Of course, TSP is a minimization problem, but it can be formalized as a decision version. So we show its decision version is hard. Of course, its optimization version is also hard. It's empty hard. Okay. All right. Okay. So next one. This one. Next one. What name should I give? Actually, let me give a definition first. Name. I don't have a very good name for this one. Okay. Weighted graph. Now we have a subset of vertices. Other than that, maybe we have a starting vertex. Okay, the question is start at S, visit each vertex inside V prime. So it's a given set of vertices and return to S. Okay, so we're looking for, say, a closed walk. You can say it's a closed walk. So we're looking for a closed walk, maybe. Because repeating actually does not help. So actually it's a closed cycle. Okay. But we can say walk or tour. All right, we're looking for such a walk. Of course, we want such that its total length is minimized. Okay, so we have a length constraint as well. So that's a problem. So I give you a graph, and you have to visit some vertices. So I give you a graph. It's weighted, okay? So I will ignore these weights, otherwise too messy. So maybe a starting vertex is here, that's S. And some vertices we must visit. So some vertices I use green ones. I must maybe visit these two vertices. All right. So looking for shortest path, a closed path actually. So actually it's a cycle. Starting from S. So maybe we do things like this, get this one, and this one, then this one, then return. All right. So that's a problem. Actually, a few years ago, Huawei posted this one in one of their contests. I think Huawei, some kind of contest. A few years ago, I forgot which year. Maybe 3 or 4 years ago, there's a Huawei contest. It's a very useful problem. In practice, it has a lot of applications. Okay, so anyone see that which problem special case of this one? Hamiltonian cycle. You can say that, but actually, no, it's the shortest path, not longest path. Actually, it's TSP. Yeah, exactly. When TSP, when V prime equal V. As I said, usually we take extremal, set the parameter to the extremal case, the boundary value. All right. So of course you can say Hamiltonian cycle, but it's kind of a little bit like more like reduction. Okay. So that's a special case. Okay. All right. No, it seems it's taking much more time than I thought. But anyway, I think I will continue instead of jumping to approximation algorithm. Does not matter, okay? Because approximation algorithm will not be in final exam anyway. So just for to give you some idea, okay? All right. So this one is also difficult. Okay. These mostly are graph problem. Now I give you a couple of non-graph problems. So hitting set. So collection, let's see. All right, so we have a ground set S. So that's a ground set. So each point here represents a ground element in the ground set. And the input is a collection of subsets. So there's a collection of subsets. All right, so it's a collection of subsets. A collection of subsets. So collection of subsets. These four elements, maybe this one. All right. So the question is it possible to choose k elements that will hit every subset? So for example, if I choose this element, so that will take care of two sets, this one and this one. If I choose this one, that will take care of this subset and this subset. So in this case, if I choose this one as well, so we'll take care of everyone. So I have three elements. I have three elements that will hit every subset. So that's a hitting set problem. Okay. So that's the definition of the problem. Is it clear? Now that's not a graph problem. So which problem is a special case of this one? So if we go back to our list. Great, so vertex cover. So why vertex cover? So vertex cover is a special case. The reason is vertex cover, what is a graph? This is a graph. The graph wanted edges, edge set. Edge set is two-element subsets. So each edge set is special case. So in this case, the restriction is restrict. If we restrict size of each subset inside C to be 2, what we get? Actually, a C can be interpreted as edges. So what we get is a graph. Then the graph, it's really vertex cover problem in this case. Okay. All right. Okay. Okay. There are some problems related to subset sum. For example, the knapsack problem. Recall knapsack problem. So we have a collection we have n elements, n items. Each has a value and say weight. Each has value say use vi. So what we want is find a subset of find some items with total weight at most w, and we want to maximize its value. So that's the knapsack problem. Of course, as decision version, so here we will say, instead of say maximum total value, we want total value to be at least v. Okay, so input other than z2 will have w and v, these integers. So of course, everything here integers. Okay, so everything here will be integers, say positive integers. So that's a say knapsack problem. Okay. So is there any problems that a special case of this one in our toolbox? Actually, only one problem that deal with numbers. That's subset sum. That's only one. Subset sum will be special case of this one by setting value equal weight. All right. So then W and V will be also same. So that's our target sum. So subset sum is a special case of this one. Okay. All right. Okay, that depends. In this case, you can item repeated is all right, so not matter because for each one give a value and a weight. So even item same, but the value and weight are different way regarded as different items. Okay, depends how you specify it. It's a technical thing. By specifying this way, then you can say item can be repeated. Also, sorry, you mean that one, then it's not repeated. We can only choose item once. Sorry. Okay, I'm thinking of something else. You are thinking about whether we can choose same item several times. But no, in that case, no, only once. Yeah, because in the textbook, I recall there are two different versions. Okay, so here refer to the version that we can choose each item only once. Okay. Okay, so let me finish with one more problem. Yeah, it's run much longer than I thought. Edge packing. All right, so input again is a graph G. Two integers. All right, so it's a packing problem. We want to put as many edges as possible using minimum number of vertices. All right, so let me give you an example. All right. So for example, maybe L equal 4. So I want to put 4 edges inside this graph using minimum number of vertices. So let's see. So one way to do it is I use this edge, say this edge, this edge. So I use 8 vertices. The largest number vertices I can use it will be 2K. 2L, because each edge will be incident with 2 vertices. All right. So now we want to use as fewer vertices as possible. Of course, this is not a solution. All right. So for example, there are other ways. Then I can use less vertices. A path is not good. For example, a path. If you use this path, 1, 2, 3, you use 5 vertices, right? Okay. So here I can use 1, 2, 3, 4. So that's only use 4 vertices. All right. Now this one is not easy. So the answer is very simple. Again, the answer will be very simple, but it's may not easy to come up with this one, because you really need to look at the problem from a different point of view, from different perspective. But normally it's difficult to change the way you see things, the way you see other things. It's a kind of dual problem of this one. So it's a clique problem. It's special case when set L to be K choose 2. So I want to pack K choose 2 edges. I want to put this many edges into a graph using minimum number of vertices. It's not hashtag here. Here means number, okay? So what do we get? I too want to put edge as dense as possible, put them together. So what do we get? We get a clique. Because a clique use K vertices to produce K choose 2 edges. Okay, no, vertex cover does not work. No. Packing, I think the only problem I can think is the clique. It's a dense subgraph. So really, packing, when you pack things, you want to put as many things into a box as possible. So here is exactly the same thing. We want to pack edges. Here, resource is vertices. We want to consume as few vertices as possible. So the best way is a clique. Because, for example, for 3 clique, for 4 clique, we use 4 vertices, but we can put 6 edges inside. No other graph on firm vertices can put 6 edges. For 10 edges, so it's a 5 clique. Only a 5 clique can contain 10 edges. Other graph with 5 vertices cannot contain 10 edges. So I give you 10 edges, you have to use at least 5 vertices. Otherwise, it's not a clique. If it's clique, then 5 vertices. Otherwise, it's not clique. So you use more than 5 vertices. All right. Okay. All right. So I think I will stop here about NP completeness. I hope you have a taste of how to prove that the problem is NP complete. Actually, how many problems you see for time so far for NP complete problem you've learned up to now? Actually, I think you've seen about 20. It's 20 already, roughly. So that should give you a good idea. From another about 10 from homework. So total is almost 30. So I believe you should have a feeling about NP completeness already from these about 30 problems, different problems. All right. As I mentioned earlier, that final exam is up to here. So final exam, everything up to here is maybe in the final exam. Okay. After that, just for the fun. It will not be in the final exam. All right. Okay. Any question about NP completeness? Okay. Good. Okay. Now, so we know that a lot of problems are NP complete, but actually, that's just the beginning of the end. We cannot just end here. Suppose you need to solve a problem and you prove that the problem is NP complete. Then what? You cannot say just because it's NP complete, I cannot do anything. Then your boss will fire you. Right? If you cannot do anything, why do I need to give you money to do the work? So you still need to do something even when the problem is NP complete. So we need to cope with the NP complete problems. So next thing we'll talk about how to deal. Actually, it's just start. Okay, really, when the class ends, then we just start. How to. So proving that a problem is NP complete actually is the beginning of the end. I should not say it's the beginning of the end. It's also not end of beginning. But anyway, it's you need to start to do something new. When you prove a problem is NP complete, we still need to solve it. So we still need to solve it one way or another. Still need to solve it. When pi is NP hard. You cannot just stop, say, because it's NP hard. Okay, that's it, I quit a job. Of course, you still need to solve it. So usually, how can we solve a problem when it's NP hard? We need to find a way. Typically, there are three different approaches. One is approximation. Actually, it's a huge area. There are graduate course dealing with approximation algorithms. So I think I will be able to give you one or two examples. All right, today maybe not, maybe on Monday. Okay, I don't know. I said only from 5:30 to 6:30, maybe. So I will have a makeup class Monday, coming Monday, 5:30. In the morning, because that's the actually FYP presentation day. So I'm kind of fully occupied until 5:15. So after that, I think I will spend some time. So 5:30. Most likely it will be more than longer than this one. I don't think I will finish by then, but maybe by 7 or something. I really don't know. Okay, you can leave anytime. If you're interested, just join. If you don't, just forget it. They will not be in the final exam anyway. Okay, it's just for fun. It's not mandatory, and I will also record the lecture. Okay, approximation algorithms. Second one is FPT algorithms. FPT algorithms. Actually, in the coming year, I will offer a graduate course that will basically devoted to FPT algorithms. It's also worth at least one course to talk about this one. So you see, that's the reason we cannot talk too much about approximation algorithm and FPT algorithms, because that's really cover a lot of things. All right. And third one is special cases. All right. So in practice, when the problem is NP complete, but usually we really need to solve in your applications. Maybe input is really special. It's not a general case. For example, we know vertex cover is NP complete, but the graph maybe you need to deal with is bipeptide graphs. So we only need to consider vertex cover on bipeptide graphs. So that's a special case. Or even easier, maybe just on trees. So we know we already know how to solve it for trees. For bipartite graphs, actually, it can be solved in polynomial time by using matching technique. So that's special cases. Typically, there are at least these 3 different ways to deal with an NP-complete problem. All right. So let me talk a little bit. We'll start about the approximation algorithm. Okay, I'm running out of the. Oh, okay, still some empty page left. All right, so let's talk about approximation algorithm. For example, vertex cover. All right, so of course, the problem we need to solve is optimization problem. We need to find, our task will find minimum size vertex cover. That's our task, but it's anti-hard. So in practice, it may be good enough to find a small size vertex cover. That will be good enough. Instead of finding the minimum size vertex cover, we find a small size vertex cover. So that's called approximation. Instead of finding minimum size vertex cover, we find a small size vertex cover. Now, typically, it's easy to come up with an approximation algorithm. It's very, very easy to come up with an approximation algorithm. Yeah, very good question. What do we mean by small? Okay. I'll talk about it in 30 seconds. Okay. Approximation algorithms. So typically, it's very easy to come up with an approximation algorithm. Actually, even a very efficient approximation algorithm. The difficult part is its analysis. Difficult part is analysis. So it's related to your question. What do we mean by small size? How do we measure the quality of an approximation algorithm? That may be difficult. All right. So let's consider 2 approximation algorithms for vertex cover. I give you 2 very simple algorithms for vertex cover. So that's algorithm 1. All right, so here I give you 2 approximation algorithms, both very, very quickly. All right, so let me show you how it works. Okay, so for example, for this graph, algorithm 1 just arbitrarily pick up the edge. So suppose I pick up this edge. So what we do is put both vertices into vertex cover. So that's first algorithm. Second algorithm is more smart. So first algorithm very dumb, actually very stupid. Just arbitrarily pick up the edge, put both ends into solution. All right. So second algorithm is clever. So by choosing a vertex of maximum degree. So in this case, I guess is this vertex. because it covers more edges. We want to use as fewer vertices as possible. Yeah, great. Yes, that's you can say second way is greedy. Actually, there are many different greedy algorithms for vertex cover. So that's one of them. It's greedy. All right, because it covers more edges. Of course, it's reasonable to add this one into solution. All right. Then we delete these edges. We delete all these edges. In the remaining graph, we do same thing. In the remaining graph, we do same thing. So then choose this vertex, and then we delete all these edges, and so on. All right. So it's very easy to see both algorithms run very fast, but which one is better? So again, what do we mean by small? How do we measure the quality? Intuitively, I guess everyone agrees 2 is better, right? Intuitively, everyone I think will agree. Anyone that disagrees that 2 is better than 1? In practice, 2 is much better than 1 in practice. But in theory, in the worst case, actually 1 is better. 1 guarantees that any solution will be no worse than twice of optimal solution. 1 can guarantee this one. But algorithm 2 can only guarantee actually it's log n OPTG. Actually, it's worse. In the worst case, actually algorithm 1 is better than algorithm 2. So in practice, algorithm 2 is much better. So worst case, so the solution you obtain in the worst case, if you're lucky enough, even in one you always get if the minimum size is k, you always get a 2k. You use less than 2k verses, but sometimes you can be lucky. For algorithm 2, if you're lucky, you maybe only use 3 verses, but if you're not lucky, you can get log n times k. Okay, I would talk more into this on Monday. Okay, because of time. All right. Okay, I will finish with 2 things. Okay, I finish with 2 things. Recall that in the very beginning of the week, I give you a very simple algorithm. Randomly mark each vertex and then return output name of marked verses as output. So M is marked verses. All right, so neighborhood. So eventually we'll have some marked verses. So these are marked verses. So these are marked verses. And the neighborhood will be these verses adjacent to marked verses. So output will be this one. In the very beginning, I give this algorithm. Very surprisingly, this algorithm actually can solve actually there's a randomizer algorithm to solve k-vertex cover problem. When graph contains a k-vertex cover, this one will able to find a k-vertex cover with probability at least 4 to the power minus k. Of course, the reason is not obvious, but the result is quite simple. All right. Actually, that's my own work. I'm very proud to obtain this algorithm. There's something very interesting involved in in the theory behind it. So actually, that's give us a very, very simple algorithm, but it's very powerful. So it's related to FPT algorithms. All right. So I think we finish with just one more. Okay. With 4 very old Chinese wisdom. Okay, let me draw it like a seal, maybe. Okay. Oh, okay. No, this part is not good. All right. So in English, my translation is just by translation, English translation, as simple as axioms. So I will finish this lecture with these 4 very old Chinese wisdom, as simple as axioms. So really, even when we design algorithm, we often think about efficiency. We want to make the algorithm as fast as possible. Actually, we are looking for shortest path. So shortest means simple in a sense. So really try to think in simple ways. Try to get things done in most simple way you can come with. All right. So I think that's it. And on Monday, I will talk a bit more, maybe a lot more on approximation algorithm and FPT algorithms. Okay. So that's it. I'll see you in the final exam if we will be online. Otherwise, I will not be able to see you. In a face-to-face exam, will not be there. All right. I don't think you want to see me again next year for this course. Okay. My personal feeling is not. My personal feeling is P not equal to NP. But you never know. Who knows? Maybe the Turing Church thesis is not quite right. There's something very strange, very powerful, like quantum computer. Actual quantum computer is not powerful enough. Maybe something you never know. But in the current model, Turing machine model, my feeling is not P not equal to NP. All right. Okay. Okay. Yeah. If you really like algorithm, I really encourage you to take the graph theory, graph algorithm course for the coming year. Usually, a few undergraduate students will take that course, and usually they will get A or A minus. Graduate students usually they don't get A or A minus from that course, but undergraduate students do. Okay. Yeah, I posted 2 different final exams in the course homepage, just for you to get a feeling. The style will be more like the older one, 2013 one. It cannot be multi-choice because of online ones. I should be more careful. All right, if we just face-to-face, then the 2018 one will be okay. Actually, it's not that simple, that multi-choice. It's even more difficult to come up with these problems. It takes much more time to design this type of question. Okay. Cheat sheet, actually it's an open book, but I really strongly recommend you to prepare a few pages instead of take notes and the textbooks. That will not help you. It's you better prepare do a review, prepare something for these important problem matching to at least for these problems. All right. Oh yeah, anything. It's an open book. You can take anything. I don't think computers are allowed. Computers are not allowed. But any paper material, you can take them. But as I said, it will not really help you. It's better to prepare 2 or 3 pages of important things. So in case you forget something, you can quickly find it. Otherwise, you have no way to find them. All right. Okay. Oh yeah. All these information for online exam will be announced in the course homepage. It will be again use Zoom meeting. Next week After we submit homework, everything is done, then I will post the full information about final exams. Starting this afternoon, I may post something. All right. Yeah, calculate whatever you like. It's open book. No, you should handwriting. Answer on the face to face should be from face to face. Of course, you handwriting. For online one, you need to write on write answer by your head. It's handwriting. You cannot use the iPad. Again, the reason is to prevent possibility to reduce the possibility of cheating. All right. To be frankly speaking, it does happen. The other course last year, I think about 50 students were caught cheating in an exam. I was in a faculty disciplinary committee for years, so I know all these things too well. As far as final exam is concerned, actually 7 problems, these 7 or 8 seed problems will be good enough. Of course, to really understand NP completeness, the more the better. All right. Yeah, so not from computer science department, other department. Yes, over 50 students. Actually, for computer science department, there were course, 12 students were caught, and all of them get demerits because I dealt with that case when I was in the FDC. Yeah, from final online exams. Online exam. So all of them failed. Plus 1 permanent demerit, I believe. For final exam, I think it's a permanent demerit, not removable. Okay, any other questions? If not, that's it. Yeah, exactly. Yeah, last year. Yeah, last year I think. Yeah. The academic honors is really it's extremely important. Okay, so I don't know what you mean by set. I think personally, I really think we need to enforce that. It's extremely important, more than knowledge. Honesty is more important than knowledge. Yes, they shouldn't have cheated. Yeah, exactly. Okay. So I'm not sympathy towards such behavior at all. You see, I was in the committee, FDC, so I dealt with many cases. I have no sympathy at all. Regarding academic audits, I think we have to be as strict as possible. Really, honesty is more important than knowledge. You can be a decent person, at least, right? If I don't know something, if I fail the course, it's all right. But if one is dishonest, then you cannot be a decent person. Yeah, yeah. On the online exam, you can use paper notes, anything, any paper material, but you cannot search internet to find solution. Actually, when I designed these problems, I think I'm almost sure you cannot find the answer from internet. So because it's hard to control for online exams, so I have to take all these into effect. Whatever I think it may happen, I have to think about these things. All right. Okay. No, actually, it's not that difficult. I think it's the average. I think my expected average for final exam is 65, or even maybe even higher. But this year, as I said, because we did not have midterm exam, so I did not have a good feeling as years before. For exam, yeah, definitely good enough. These problems, 7 problems will be good enough as far as final exam is concerned. So any more question about final exam? For the time being, they are same, but I always have right to change something in the for the online exam paper in case suddenly I think maybe something I better to change it. But even I make some changes, but the level I think will be very, very similar, will be very close. It's possible I make some changes to the online version. Oh yeah, 40% at least to pass the course. Actually, as I said, it's really anti-hard to obtain below 50 marks from final exam, as far as I can tell. If you cannot get 40 marks, actually, I don't think you should be in computer science, to be frankly speaking. It's not a discipline for you at all, to be frank. All right. For these, it's hard to say. I cannot tell for the time being. I have to see the results. Then I will decide, because we still need to follow the curve, I think, basically. Oh yeah, another thing I nearly forget. Yeah, 20 marks. For some question, I think Sarah, okay, I'm keep telling you more about final exam. There are 7 problems, I think. For 4 of them, 3 to 7, I believe. If you some contain some sub problems. For those, if you don't write anything, if you just say I don't know, you get at least 20% of the marks. All right. As I told you, I learned this one from Steve Cook. At least you know something. You know I don't know, right? This is more than you don't know that I did something wrong. I don't know I did something wrong, but at least you know something is wrong, or some I don't know. I don't know. I don't know. I know I don't know. Okay. So you deserve 20%. Now look, you only need another 20% to pass the course. It's really too easy. All right. That's why I said it's really anti-hard to get below 50 marks. Of course, to get 80% or 90% is not easy. Be careful with the problem with only very low marks, say 3 marks or 2 marks. If there's such a problem, usually that means the problem is difficult. Towards the end, especially. So these are not easy problems. Usually a problem with the high marks is easy problem. Say 10 marks for a problem. Usually it means the problem is really easy. So most of you will be able to do it. But there are a problem with 3 marks. No, nothing to scare. Okay. So those are only for these problems, really for those who really think they're excellent for this course, then they will need to solve such problems. If you want to get an A or A minus, you need to solve such problem. Actually, solutions are not difficult. All the solutions, I think at most, maybe 4 lines or 5 lines. All of them, all the problem, each problem maybe take at most maybe 3 or 4 lines. Even the difficult one with 3 marks, yeah, also 3 or 4 lines, I think. But of course, it may not be easy to come up with an idea. No, I cannot. I did it. Okay, I did it several times. I'm the only one. But as I told you, somehow, I don't know why, usually I have a very good feeling that like average, from my previous experience, usually very close, within 5%, or even closer. Oh yeah, most of the problems are easy. As I said, 50 or 60 problems, 50% or 60% of problems are really easy. A solution will be posted after coming Wednesday. Thursday by noon, I think. I asked Tia to post the solution for homework 4 by noon of April 29th. All right. Okay. In this case, actually, because these solutions are very, very simple, pseudocode. Yeah, exactly as you said. Yeah, that's the principle in the final exam. Okay. Yeah, so it will be as simple as axioms. So even pseudocode, very simple pseudocode or very simple, clear explanation, use English sentence will be okay, because these solutions are very, very simple, just 1 or 2 sentences. So it's really very easy. Of course, you always have a question mark when I say easy, okay? Because it's more like a mathematical course. You can always doubt what I mean by easy. What I can say is solutions are very easy. All of them are easy. But of course, as I said, you really need to know. For example, reduction from 3 sets to vertex cover. Let me tell you again and again. It will be in the final exam. Of course, maybe not in the exact same form. Okay. Yeah, either question can be very hard, of course. Okay, so that one will be in the final exam. So what I mean is, it's not good enough. You just remember reduction. You need to understand why we do reduction this way. If you just remember the reduction, maybe you can get some marks. But in order maybe to get full marks from a question related to the reduction from 3 sets to vertex cover, you need to understand the principle behind it. Just as one problem in the homework, you need to do that one. Recall, that's why I give you a problem in the homework, ask you to mimic reduction from 4 sets to vertex cover. So you really need to understand the idea behind it. That's more important. Just remember that the result is not good enough. It's not yours. Eventually, how do you know you learned these things? Only when you can explain to other people clearly, then maybe you know these things. Once it becomes yours, then you know these things. All right? Okay? So if I stay here for long enough, perhaps we'll tell you, maybe I will tell you every problem in the final exam. Perhaps we should stop. Okay. All right. Okay, good luck. So hope to see you on Monday, and also maybe in graduate course, graph algorithms. If you like the way I teach, otherwise, please don't bother. If you don't like the way I teach, if it's too mathematical, then please don't show up. Okay, to make all of us happy. Okay. All right. Bye bye. Take care. Bye bye. Thank you all. Bye bye. The tutorial today. And next week, tutor will upload solutions, a tutorial about solutions, because next week it's hard to predict whether you will be free or not. So it's we don't fix any time, but solution will be uploaded as a tutorial. All right.